just like with the inverse function theorem, our goal with the implicit function theorem, or our method to prove it, will be to apply linear algebra to the derivatives of things. So the derivative of a function is a linear map, which is a linear approximation to the function near various points where you evaluate the derivative. So what we're going to do is apply linear algebra ideas to the derivative and then try to use analysis to carry those ideas from linear approximation to actual function. Okay, so then it makes sense to first understand the linear situation well. So understand the linear situation well, assuming that, say, the linear approximations are perfect approximations. Understand that situation well, then bring in the analysis. So for this first portion, it's basically just going to be linear algebra. So think of this video as the implicit function theorem for linear functions. Okay, so before we can really efficiently state things here, we need to introduce a bunch of notation. So the first bit of notation, if you have an n tuple x and an m tuple y, then we're going to, so you remember in the last video I kept talking about pairs xy in the xy plane, right? And back in that video, x and y were real numbers. In general, x and y can be tuples with different numbers of entries. But we still want to talk about pairs xy, except the pairs xy, instead of living in R2 like here, they're going to live in Rn plus m. So for convenience of notation, we'd like to still write them as pairs, but what you're supposed to understand when we write a pair is that it means this. It means x1, x2, etc. all the way up to xn, and then y1, y2, etc. all the way up to ym as an n plus m tuple. So just in the last previous video, we just had n and m both being 1. So pair xy just stood for something in R2. Okay, and the next bit of notation is about linear maps. So let's say L is a linear map from R n plus m to Rn. Okay, then how would you imagine L as represented by a matrix? And actually, I just had a look in Rudin and remember that he uses A for his linear maps. So let me just stick with that notation, just to be consistent between lecture and textbook. So let's say A is a linear map. So how would it look as a matrix? If it can be represented by, in the standard basis, or any basis, it can be represented by a n row, n plus m column matrix. So think short, fat matrix. So n rows, and then there are n columns here, and then m remaining columns. So a short, fat matrix, fatter than it is tall. Then what we'd like to do is describe two linear maps whose representations are given by basically cutting this matrix in half and looking at a square submatrix here, an n by n, square matrix here, and over here an n by m. Not necessarily square, but maybe square matrix. Okay, so how am I going to do this? first of all, in order to do this cut, we're going to insist on standard basis, or at least how to phrase this. I guess you can use any basis you want for Rn, and any basis you want for Rm, and then combine those two in a suitable way by embedding Rn and Rm appropriately into Rn plus m, and then getting a basis for Rn plus m in that way. That would be sufficient. But you know what? Forget it. The trying to do this in terms of bases and matrix representation is not exactly the best. So instead I'm going to follow how Rudin defines it, but just imagine if you're representing things in the standard basis, if you just use the standard basis, which you don't necessarily have to use exactly that, but if you use the standard basis, then what we're doing is cutting the matrix so that we have two matrices, basically, a square one and n by n one, and then a not necessarily square one. So here's the idea. We are going to define two linear maps. Given A, a linear map A, define a linear map A sub x and a linear map A sub y. A sub x is going to be a linear map Rn to Rn. So it's going to end up being the one whose representation in the standard basis is given by this submatrix, and A sub y is going to be a linear map from R M to Rn, and it's going to end up being the one whose matrix representation in the standard basis is given by this submatrix. And what's the definition that achieves this? Is this. A sub x, okay, so what do you apply A sub x to? You apply it to a vector in Rn plus m, right? So we're going to say if you apply it to h, comma k, then, I'm sorry, you don't apply A sub x to vectors in Rn plus m. You apply A sub x to vectors in Rn, like h. We're going to say when you apply it to h, then what you do is you apply A to h comma 0, where by h comma 0 I mean the vector that goes h1, h2, h3, etc., h sub n, so like this, h1, h2, etc., h sub n, and then a collection of m zeros, like that. So that's what I'm plugging in there. Basically, I'm using this notation, and I'm saying this is h and then 0, so this part is h and then this one is 0. Okay, hopefully that's clear. And I hope you can kind of see how that is cutting the matrix like this. I mean, if you think of A as represented by this matrix in the standard basis, then h comma 0 would look like the column vector, would have the representation, the column vector, h1, h2, etc., hn, and then 0, and then you have m zeros here. And what happens when you apply this matrix to that column vector, assuming everything's in the standard basis? Well, what you get is a column vector with n entries, right? If you think about the matrix, the mechanics of matrix multiplication, you get a column vector with n entries, which is given by applying this submatrix here to just the h part here. And this submatrix gets applied to the 0 part, so nothing happens. So a good way to summarize the mechanics, actually, the mechanics of matrix multiplication, is that no. Okay, I'll give you the summary after I make these definitions. So define A sub x like this, and A sub y like this. So A sub y of k is going to be A of 0 comma k. So same idea, but go 0, 0, 0, 0, and then k1, k2, etc. up to kn. Okay, then what I was describing here is that when you apply this matrix in the standard basis to a column vector with n plus m entries, then it'll apply this to the first n, and then apply this to the next m, and then add the results. That's what it does. So that principle is worth pointing out. So for any vector, which you could split up as hk, for any vector in Rn plus m, we have that when you apply a to that vector, then that splits up as the first part on h plus the second part on k. And here's actually a way of just proving that, is hk can be rewritten as this sum, h0 plus 0k, right? And a is linear, so it distributes. And so this is the definition of what I'm calling a sub x. And this is what I'm calling a sub y. Okay, let me just give an example before I state the linear version of the implicit function theorem. So let me give you an example where n is 2 and m is 1. Then we're thinking of, remember, we think of x's as being in Rn, so here R2, and we think of y's as being in Rm, so here R1. Then let's say A is a linear map from R3, 2 plus 1, to R1, R2. And let's say it's given by, whenever you apply A to a 3-tuple consisting of, let's call them x1, x2, and y1, let's just call it y, then you get the following matrix applied to the column vector x1, x2, and y. So here's the matrix that I will choose. How about 1, 2, 2, 1, minus 3, 4. So say you have this setup. This is a linear function from R3 to R2. Then, and you can see we have a short, fat matrix representing it, right? So this is the matrix representing our linear function in the standard basis. Then question, the big question of the implicit function theorem is, does the equation this equals 0 implicitly define a function x as a function of y, where by x I mean x1 and x2, and by y I mean y. So does it define a function, this two-component function, x1 of y, x2 of y? That is the big question of the implicit function theorem. And here it's not so hard to see that it will work. So just look at how this splits up. So a of x1, x2, y, when you apply this 2 by 3 matrix to this column vector with 3 entries, you're going to get split it up like this. So I'm just cutting the matrix down here and taking this first square part. So you're going to get this applied to the x part plus this applied to the y part, right? So this is a 2 by 1 matrix applied to a 1 by 1 matrix, or a column vector with one entry. And if you write down the equation, this equals 0, so look at the equation, this equals 0, then yeah, that does define x1, x2 as a function of y, because this matrix here is invertible, right? So this is how you would manipulate the equation. First, let me just move that to the other side and then apply the inverse of this matrix. Inverse times whatever we had here. So the answer is yes, because when you cut this matrix and take this part, that part is invertible. So that's going to be the idea of the linear version of the implicit function theorem. It's it's pretty easy. So I think it's one of these things that's harder to state than it is to prove. And once you've stated it, it's kind of obvious. Oh, right. And by the way, it would not have been any more complicated if I made y, instead of being a real number, if I made y like be an R27 or something, then I would have just had like another 26 columns here, right? And here I would put y1, y2, all the way to y27. And instead of 1 here, it would have been 2 plus 27. And this would still be 2. And, you know, everything else would be the same, right? Like, here I would just have 26 more columns, and here I have 26 more entries, but it's not it doesn't change much. So this part can be arbitrarily high dimensional. And the argument is fine. Okay, so let's state the linear version of the implicit function theorem. Okay, so let's assume that A is a linear map from Rn plus m to Rn, and we saw in our example that it mattered to have this, what we needed was to have this portion be invertible, right? So, and A sub x, which, you know, I'm writing down a lot of matrices, but notice I'm never saying that A is a matrix. I'm being pretty careful about that. When I say A is a linear map, I mean it's a linear map. It's a function, not a matrix. So you can see I wrote A applied to this equals the matrix applied to this. That's not the same as saying A is the matrix. All right, so A sub x, let's assume it's invertible, an invertible linear map. So back here I was discussing invertibility of this matrix. Here I'm talking about invertibility of the linear map. Those are different statements, even though they are equivalent. And AX is invertible. Then we think that A of x comma y equals 0, this kind of equation. And Rudin uses h and k here, but I'm going to use x and y just because I want to make it look like the full implicit function theorem, except just the function is linear. So the full implicit function theorem is just going to have a function f here instead of x and y. And it's going to be more complicated because it's going to be focusing on, you know, like we said before, the existence of neighborhoods w and v of x naught and y naught, of some point x naught and y naught. So it's going to be more local statement rather than global. This will be global. So there's some simpler things here. Okay, so then this equation defines a function. Let me say x as a function of y. And you know, I do not want to confuse too much between, you know, okay, let me put it this way. Here's a way that people will often write x is a function of y. This is something people will often write. They will say x is x of y. X is a function of y. X depends on y. I don't like that way of writing, especially not when I'm writing down theorems and proofs. I'd rather be a little bit more picky about whether the symbol x stands for a function or a variable. Like a, when I write x, I often mean an n tuple, right? But when I write x as a function of y, then what's x? It's not an n tuple. It's an n tuple valued function. I care about that distinction. So in order to keep the distinction, I'm going to use a capital letter X to stand for the function x of y. So I'm going to say defines a function capital X Rn to so this will be, sorry, it's going to be a function that you input y into, and it gives you x's back out. So Rm to Rn, yeah, such that if you put in this function here, yeah, I just thought of a better way of stating this. How about I make two statements. One kind of sloppy colloquial statement and one more precise statement. So on the one hand, I'll say then this equation defines x as a function of y. In quotes. And then I will clarify what I mean by that. That is, there exists an x such that this is true for all y. There. So that's the linear version of the implicit function theorem. And as you will see, the proof is nothing. The difficulty is just stating it and interpreting what it means and deciding that this was something we needed in the first place. So assume the hypotheses. Then how are we going to define this function? Well, it's the same principle that we carried out here. Split up the way A operates on x comma y as A sub x, this submatrix, applied to the x part, plus A sub y, this submatrix, applied to the y part. So let's see, for any xy in R n plus m, we have, when you apply A to xy, it splits up. So it splits up because of this principle that we came up with here. A applied to hk's, this part applied to h plus that part applied to k. That's the same idea as the split here. This submatrix applying to the x's and that submatrix applying to the y's. So we have, this is A sub x applied to x plus A sub y applied to y. And now I'm in a position to use the assumption that A sub x is invertible. So let me do some scratch work on the side, I guess. Or how about I do the scratch work here and then I'll erase the scratch work. So I want, let's do scratch work in blue. I want 0 equals I want capital X to satisfy this. Sorry. I want capital X to satisfy this, which is this. Right? So that means I want this. That tells me exactly what capital X has to be, because a sub x is an invertible function. So that tells me capital X I can even phrase this without y's, right? Without the little y's showing up. This is basically what I want, right? So then that tells me exactly what capital X has to be, because this is an invertible function. It should be a sub x inverse composed with negative a sub y. Or in other words, negative a sub x inverse composed with a sub y. So that tells me what capital X should be. Okay, so now let me erase the scratch work and fill it into the proof. I also just realized this should be part of the theorem statement. Not just that there exists an X, but that it's this. This is X. Yeah, so let me... Oops. Okay, let me fumble with this for a bit. Okay, so let me add to the theorem statement. By the way, X is just that. Okay, now proof. Define X to be that. Then let's prove that this works. So then A of X of y is A. Well, first split things up. So that's A sub X of this plus A sub y of that. So that's using this principle from before over here. And then this is negative a sub x inverse a sub y, y. And you can see these cancel and you get 0. Okay, so that's the implicit function theorem linear version. So what's going to change, what we're going to do next time, is we will do this but not assuming A is linear, and we won't call it A, we'll call it F. And the domain will not necessarily have to be exactly this, it'll be just some open set, a subset of Rn plus n. And the equation will be f of xy equals 0, but f will not necessarily be linear. And instead of assuming that f is in some way invertible, no, we're going to focus on the derivative of f, and then take, the derivative of f will be represented by a matrix, and then we'll take that first square part, or, do this. So we'll assume something like this, but about the derivative of f. And the conclusion will be a little bit more complicated because it won't be something global like this, where there's just this global x that works. No, it'll be more like there exist these neighborhoods where certain good things happen. And the proof will not be so difficult. Like the inverse function theorem proof was a lot harder. With the implicit function theorem, I find the main difficulty is stating it and understanding why such a thing is so useful. I hope this has helped you see why it's so useful. I mean, doesn't this happen a lot? A situation where you're trying to define, where all you have is an equation and you're trying to use the equation to define one thing in terms of another thing.